Welcome to this video on stress functions for the calculation of cross-section constant and stress in Saint Venant torsion. This is one of several videos in a short course on cross-section analysis posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. There are a number of quantities that may be of interest in a cross-section analysis. Many of them are shown on this slide, but the scope in this video is more limited. Specifically, the objective is to establish stress functions, known from Saint Venant theory, in order to calculate the cross-section constant, J, and also the shear flow and shear stress in the cross-section of beams subjected to Saint Venant torsion. The next slide gives an overview of the boundary value problem that was developed for Saint Venant torsion in the short course on structural members. As usual in the notes posted at terje.civil.ubc.ca, Toolbox, equilibrium and section integration is on the left-hand side, kinematic compatibility is on the right-hand side, and material law to link the two sides is at the bottom. As we saw in the development of Saint Venant torsion, the theory is formulated around the concept of a stress function. Stress functions applied in the theory of torsion was pioneered by Prandtl, and the stress function is denoted by the letter P on this slide. Notice that the stress function takes the place normally occupied by the stress itself. Also, notice that this boundary value problem is formulated in terms of shear stresses, which are obtained from the stress function by simple differentiation. Have a look at the video on Saint Venant torsion in the short course on structural members for more details. In this video on cross-section analysis, we start by identifying the two key equations in Saint Venant theory. One is marked with a solid black line and says that the torque on the cross-section is 2 times the volume under the stress function. That is the section integration for this boundary value problem. The other is marked with a solid red line and combines material law and kinematic compatibility, again formulated in terms of the stress function. For now, we will ignore equilibrium with the externally applied distributed torque, mx, but rather observe the general expression for the relationship between the torque, T, and the rotation of the cross-section, phi, marked with a blue circle here. The colored equations are copied over to the next slide, where we develop an expression for the cross-section constant, J, for Saint Venant torsion. Notice the two different notations for the derivative of the rotation, phi, and notice that when we solve for J, then we arrive at the expression at the bottom of the slide. To obtain this neat expression, we have denoted the volume under the stress function by capital V. We have also denoted the sum of the double derivatives of the stress function with respect to y and z for nabla squared of p. That expression will be utilized later in this video. The next slide develops an alternative expression for the cross-section constant, J. This is done by first integrating the differential equation that was earlier marked with the red color. This is done in the first equation on this slide, where the Greek symbol capital lambda denotes an arbitrary closed path in the cross-section, and a lambda is the area within that path. Integration by parts applied to the left-hand side is carried out in the second equation shown here. Next, we introduce the shear stresses, because they are simply the derivatives of the stress function. We substitute that result back into the left-hand side of the first equation, which gives the equation marked with green here. From here, we follow the same path as on the previous slide. The new version of the differential equation is substituted into the right-hand side of the template equation for Saint Venant torsion. The left-hand side remains what it was on the previous slide. Solving for J gives the expression shown at the bottom of this slide. We will return to the calculation of the cross-section J, because we will now address specific cross-section types. On the next slide, we examine thin-walled open cross-sections, such as the one sketched on the left-hand side. Thin-walled means that the thickness, T, of each part of the cross-section is significantly smaller than the length of the part. It does not matter if the parts of the cross-section are straight or curved, although the cross-sections shown on this slide have straight parts. Notice that these particular cross-sections have no cells, namely no cavities. That means they are open cross-sections, which is the subject matter of this slide. Notice on the left-hand side that the cross-sectional coordinate r is defined to always be perpendicular to the longitudinal coordinate, s, which runs along any cross-section part. Also visualized on the left-hand side is the half-cylinder stress function mentioned in the video on Saint Venant torsion. That stress function runs along every part of the cross-section and is quite simply a choice we have made, leaving us with a stress function that gives good results. The mathematical expression for this stress function, which is shown in the top equation, is visualized on the right-hand side. Notice that the amplitude of the stress function is k, and that it runs from minus t½ to plus t½ In words, this is a quadratic pillow with magnitude k that follows the longitudinal direction of all cross-section parts. Wherever a cross-section part ends, there is a minor error. The stress function is not zero at that short edge, which violates an important boundary condition explained in the video on Saint Venant torsion in the short course on structural members. However, this stress function remains appropriate as long as the thickness, t, is small relative to the length of the cross-section parts. The second equation shows the expression for the cross-section constant, J, derived earlier. Below, we evaluate the volume underneath the stress function. Notice that the product T times B in the result denotes the sum of the length times thickness of all cross-section parts. A note about cross-sections with multiple parts is provided on the next slide. For now, we proceed to evaluate the two double derivatives of the stress function. Notice the comma used to indicate derivative, borrowed from index notation. Substitution into the expression for J gives the result on the right-hand side. It says that the cross-section constant, J, for Saint Venant torsion of thin-walled open cross-sections is 1/3 times the sum of length times thickness cubed for all cross-section parts. With J determined, we address the second objective in this cross-section analysis, namely shear stress due to torque on the cross-section. We first differentiate the stress function according to the definition of the stress function in Saint Venant theory, giving shear stress only along the s-axis running along each cross-section part. We will have a look at this stress distribution on the next slide. Next, we employ the stress resultant equation of Saint Venant torsion theory, which says that the torque is 2 times the volume underneath the stress function. That volume was calculated above, and we solve for the stress function constant, K, in order to express it in terms of the torque, T, that is substituted at the bottom of the slide, which gives the expression for shear stress in terms of torque. The subscript I is introduced to identify the thickness, Ti, at the location where the stress is computed. Conversely, T times B in the last parenthesis is summed over the entire cross-section because it is part of the computation of the volume under the stress function, as mentioned earlier. That point is expanded upon in the next slide. Here we assume that the cross-section, such as the ones shown on the left-hand side, consists of parts with different thickness and potentially different shear modulus. G. The first equation states that the total torque, T, is carried by superposition of all parts of the cross-section. The template Saint Venant equation, which says that torque is Gj times phi prime, is introduced in the next equation, where it is recognized that all parts shares the same rotation of the cross-section, phi. Furthermore, it is recognized that the sum of Gj for all cross-section parts is the total Gj for the cross-section. Next, torque in each cross-section part is spelled out, again using the template Saint Venant equation. Because the rotation, phi, is shared by all parts of the cross-section, we can introduce the Saint Venant equation once more, now for the entire cross-section. The result is that the total torque on the cross-section is taken by each part of the cross-section by fraction of Gj for the part over the sum of Gj for the entire cross-section. This is an important insight that amends the calculation procedure from the previous slide. First, calculate the cross-section constant, J, for each cross-section part. Second, sum Gj over all parts to get the torsional stiffness for the entire cross-section. Third, calculate the fraction of the total torque carried by each part of the cross-section by using this fraction of Gj to total Gj. Fourth, use the section integration equation to calculate the volume underneath the stress function of that part. That means dividing the local torque by 2, as seen here. Fifth, determine the constant, K, in the stress function for that part. Finally, substitute that result into the stress formula, as shown at the bottom of this slide. On the next slide, we first examine the stress distribution along the R-axis, which is perpendicular to the longitudinal direction of each cross-section part. Because the stress function is quadratic, the shear stress, which is obtained by differentiation of the stress function, varies linearly. One may say that the shear stress circulate in the cross-section, as shown by black arrows. This is similar to the shear flow from bending addressed in another video in this short course on cross-section analysis. The figure on this slide contains two small arrows that are not part of the stress function we utilized. The stress function is a half cylinder, and the derivative of it, in the S direction, is 0, meaning there is no stress in the R direction. Let us examine this point by calculating the torque that is given by the stress function we actually used. Using the result from the previous slide, the expression for stress shown here is evaluated at T/2, namely at the very edge of the cross-section. Next, the resultance of that stress is calculated below, with a factor 1/2 to account for the triangular stress distribution, and a factor 2/3 in the moment arm between the two resultants. The result is paradoxical. It says that the torque from the stress function is half the torque that we have applied to the cross-section to calculate the stress. This result does not mean that the stress is wrong. Rather, we have forgotten the small stress contributions from the short edges of the cross-section. They are not accounted for in the stress function we used, because the stress function violates its boundary conditions at those locations. But in reality, those stresses are there, and they have a large moment arm, meaning that they contribute half of the torque on the cross-section. In Chapter 10 of their 1969 book on Theory of Elasticity, Timoshenko and Goodyear acknowledge that the small shear stresses that are here neglected can have an appreciable effect because their moment arm is substantial. They also point out that the question was cleared up by Lord Kelvin in Kelvin and Tate's Natural Philosophy book, Volume 2, page 267. Before we leave this slide, we may ask if other stress functions would be possible. The answer is yes, but many of them give stress distributions that appear unphysical. Consider, for example, a triangular stress function with its peak at the midline of the cross-section. The constant slope on the sides of the triangle implies constant stress, with a discontinuity at the middle of the cross-section. That appears unphysical. Instead, we might contemplate half a sine wave as a stress function. That would be better, but still not as likely a stress distribution as what is seen here for the quadratic stress function. On the next slide, we start the examination of closed cross-sections. Closed cross-sections have one or more cells and carry torque far better than open cross-sections. If one draws a continuous line around the circumference of the cross-section, then there will be more than one line. For this square cross-section, one line follows the outer edge and one follows the inner edge by outlining the cell. When postulating a stress function under these circumstances, the constant value of the stress function around the edge, dictated by the boundary conditions established in the video of Saint Venant torsion, may be different for each of those lines. In other words, if we set the constant value to 0 along the outer edge, then we cannot say that it is 0 also along the inner edge. The boundary condition simply says that the stress function must be constant around all free edges. As a result, a stress function with more than one unknown is needed. In turn, more equations are needed to determine the unknowns. We use kinematic compatibility to determine those additional unknowns. As shown at the top of this slide, kinematic compatibility expresses that the net axial displacement around any cell must be 0. In order to identify the infinitesimal displacement du, first let the letter S denote the axis that follows a closed curve in the counterclockwise direction around the cross-section, and let V tilde denote the displacement in the S direction. The shear strains shown in this figure helps us determine du. Notice the two contributions to the shear strain, one in the S direction and another in the X direction. Next, we introduce the material law, which says that tau equals shear modulus times gamma, and solve for du. Next, we substitute the result into the compatibility equation. Next, the displacement V tilde in the S direction is expressed in terms of the cross-section rotation, phi. As shown in the figure at the bottom, the displacement is phi times h, which is the distance from the center of rotation to the tangent line of the s-axis at any location along the closed curve. That expression for v tilde is substituted into the compatibility equation, and the term with the integral of h times ds is isolated. Next, we examine that integral. With reference to the shaded area in the figure at the bottom, the last integral is expressed in terms of the area within the closed curve, denoted by the letter A. The product h times ds is twice the area of the shaded region. That gives the new compatibility equation in the second last equation on this slide. We now introduce the template equation for Saint Venant torsion, circled in blue earlier in this video, plus we cancel the shear modulus, G, in order to arrive at the final kinematic compatibility equation at the bottom of this slide. Notice that this equation includes kinematics and material law, but not the section integration equation. Therefore, it serves a similar role to that of the differential equation that was earlier circled in red. This equation will be an important tool when we now move to the next slide. We now specifically address thin-walled cross-sections with one cell. The assumed stress function has 0 amplitude around the external edge and amplitude k around the internal edge. It has a quadratic variation in between, with m denoting the height of the parabola above the 0 to k amplitude. We let the s-coordinate run along the midline of each part of the cross-section, with the r-coordinate running perpendicular to it. As a result, the stress function in the top left corner matches the stress function marked with the green color in the figure. Two equations are required to determine the constants k and m in the stress function. To that end, two continuity equations are established. One of these could be replaced by the original differential equation from earlier in this video, but an important point about the constant, m, is better made with two continuity equations. The shear stress needed for the compatibility equations is shown next, followed by the continuity equation expressed along the midline where r equals 0. That equation is followed by continuity along the inner edge, where r equals t over 2. The result of combining the two compatibility equations and solving for m is shown here. The line integral of 1 over t is easily determined as a sum of length over thickness for all parts of the cross-section. The observation is now made that, for thin-walled cross-sections, the last two fractions in the expression are both approximately equal to unity. For that reason, the value of m is approximately equal to 0. That is the reason why we start over with the linear stress function that is marked with the blue color several places on this slide. The first observation we make about this stress function is that the shear stress in the region where the value of the stress function varies is k over t. We find that by simply differentiating the stress function, which follows its definition. Because shear stress is shear flow divided by thickness, t, as we saw in the course in the video of shear flow due to bending, the shear flow is actually identical to the constant k. Remember, there is no stress in the cell of the cross-section, where the stress function is flat. As a reminder, this slide also shows the stress resultant equation for Saint Venant torsion, which says that the torque equals twice the volume under the stress function. If we denote the area within the middle line of the walls of the cross-section by am, then this expression shows how to obtain k for a given torque on the cross-section. Finally, we substitute that result from the section integration into the first kinematic compatibility equation on the left-hand side. We mentioned earlier that this equation serves the role for closed cross-sections that the differential equation for Saint Venant torsion served for open cross-sections. The result is called the second formula of Brett, which gives the formula for the cross-section constant, J, for closed cross-sections. The integral in the denominator may look hard, but it is simply the sum of length over thickness for all the walls of the cross-section. Before we leave this slide, we observe how the shear flow for a closed cross-section is entirely different from that of an open one. In the closed cross-section, the shear stress is constant through the thickness and flows around the cell in one large loop. The shear flow is constant and equal to k around the cell. The large moment arm between these shear flow arrows explains the large capacity of closed cross-sections to carry torsion. The details of multi-celled closed cross-sections are provided in the note on Saint Venant torsion in terje.civil.ubc.ca. They are omitted in this video, but the next slide is included in order to visualize the stress distribution and summarize the cases already covered. Notice that the stress functions in the two cells of this cross-section have different constant, K. Also, notice that the stress function for the free flange is the half cylinder that we saw previously in this video for an open cross-section. The result is the stress distributions shown at the bottom of this slide. Notice the linearly varying stress and the constant stress across the thickness of different cross-section parts, which we have seen earlier. Also, notice the subtraction of shear flows from adjacent cells in the wall that separates them. This video has presented equations suitable for hand calculation of cross-sections in order to find the cross-section constant and stress. In modern structural analysis, it is also possible to carry out these calculations on the computer, using the finite element approach. Many structural engineers are familiar with the finite element method for the analysis of structures discretized into different element types. That is covered in terje.civil.ubc.ca Toolbox in the short course on the finite element method. However, it is also possible to use the finite element method for cross-section analysis. In the context of Saint Venant torsion, the derivations needed to apply that computational approach to generic cross-sections are provided at the end of the document on Saint Venant torsion posted at terje.civil.ubc.ca Toolbox. In fact, the finite elements page of that website provides freely available Python code to carry out such demonstrations. In addition, a Python code is provided in terje.civil.ubc.ca Toolbox to carry out the hand calculation approach presented in this video in an automated way on the computer. Have a look at the computational cross-section analysis portion of the finite elements page at terje.civil.ubc.ca Toolbox. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.